So my name is Andrew Collette. I work at the University of Colorado Boulder, and I'm talking about two things that have really influenced my career as a scientist. One of which is Python, of course, and the other one is a technology called HDF5. So you've been here for a couple of days at the conference, and I imagine that you heard in one session or another the name HDF5. But probably as like a footnote in somebody's talk where they say, we did all this cool stuff, and then, oh, by the way, we stored the result in HDF5. But HDF5 is really much more than just a file format. And what's interesting is, even in the 6 or 7 years that I've been doing scientific Python, HDF5 has really exploded in use. So right now, there are over 100 projects on SciPy that are using HDF5 technologies in some way. And what's really interesting is if you look at the two major bindings for HDF5, PyTables and H5Py, together they are over 30,000, about 30,000 downloads a month. And so there's something going on here. And what I want to try and do in this talk is to explore why I find HDF5 a useful technology for myself as a scientist, and also talk about some upcoming features that I think will be of interest to the community as far as using HDF5 in a parallel context. So we'll back up a little bit here. I'll give you an idea of my background for this. I work at CU Boulder in a laboratory which is funded by NASA to investigate the physics of high-speed dust impacts. So that means micrometeoroids in space smashing into spacecraft, planetary surfaces, and they gave us a few $million to build an accelerator facility that will fire micron and submicron sized dust particles into fixed targets at space-relevant speeds. That means tens of kilometers a second, hundreds of thousands of miles per hour. So as you might imagine, this facility here generates quite a bit of data. Every impact, you get the speed of the particle, the mass of the particle, along with a wealth of experimental data. And so we had to find a container format for data when we were starting out the facility, and so we chose HDF5. And what's interesting is, if you look at kind of our analysis pipeline, this is a small lab, so maybe a dozen people, we got external users. So we have kind of a typical analysis pipeline. You might imagine that at one end of the pipeline, there's kind of the raw archival data. This is incredibly valuable stuff. It comes out of the accelerator. It's got the raw information on the speed, the mass, scientific data, the waveforms. So this has to be stored in some kind of a medium that is going to be accessible 5 years from now, 10 years from now, 15 years from now, in a way that can be read into Python or IDL or MATLAB or any other analysis language. So that's kind of stage one. You go down the pipeline a little bit. This is, I call this the iterative step. This is what you do on your laptop or your workstation as a scientist. You get your experimental results, and you're not really sure what to do with it at first. So you get the raw data, and you go through many, many stages of analysis. The data will change shape, it'll change format, it'll change type, and so you have to have lots of flexibility at this stage of the pipeline. And then finally, when you've finished all of your analysis and you're ready to share the result, you need to have a mechanism for doing that. And so generally speaking, that's like a figure in a journal article. But increasingly, that means packaging up some reduced data set that you share with your colleagues. And it's extremely important that this be portable. Not only do people use other analysis environments, but also all the information to make sense of the data needs to be in that file. So if I have a time series, for example, I need to know the spacing and time between samples and when it was acquired and all that stuff to make sense of the data. So a complete data product that went into the pipeline. And what's interesting about HDF5 is it's a technology that addresses every stage of this pipeline. HDF5 has been used by NASA for years. There are petabytes and petabytes of data in HDF5, so for archival purposes, the question is pretty much answered as far as I'm concerned. There's no risk in storing the data in that format. I'm going to show you later on in this talk how HDF5 and Python together can address this iterative stage in the middle, where you're not really sure what format your data should take, and it's evolving very rapidly. And then finally, of course, HDF5 provides a native mechanism for storing your data and your metadata together into one package, which makes it ideal for sharing with people. So first of all, what's HDF5? First of all, it's a file format. Okay, that's people usually encounter it. If you talk about, like, for example, pandas is a way you can store a data frame into an HDF5 formatted file. It is also an enormous C library maintained by the HDF group and associated to a large API. And the great thing about this is, because it's written in C, you can talk to it from anywhere. And so Python's got bindings, MATLAB, IDL, other packages have got bindings for it. And the great thing about it is that HDF has taken over the responsibility for maintaining this thing. And so you will pretty much always use HDF5 through an intermediary. Sometimes that means H5Py, for example, in the Python landscape. Sometimes it means a top-level product like pandas. but you never need to actually talk to HDF5 yourself. And the third thing that makes it work is a simple object model. It's incredibly simple. This is why it's so useful and flexible for data analysis. So the object model in HDF5 is basically three things. So number one is called a data set. You imagine you wanted to take a NumPy array and store it to disk in a way that you could retrieve it later without worrying about byte swapping or escaping or anything like that. This is what you want to use. So a data set is basically a NumPy array on disk. It is extremely scalable. It is very common in HDF5 to have data sets that are many terabytes in size. And of course, you can't load that into memory, and so HDF5 provides native mechanisms for slicing. You can retrieve from the data set only that piece of information that you want. So if you want to do a block-oriented analysis, for example, on a 10 terabyte data set, you can do that. There's also a whole series of features for data sets that I'm not going to mention here, one of which is compression. This has been a lifesaver for our laboratory. Because of the data that we use, we are able to achieve compression ratios approaching 50%. And so if you look at the amount of storage space that we need for this stuff, it's been a really useful thing. So it's also not uncommon in HDF5 to have tens of thousands of data sets stored in one file. And so you could dump them all into one namespace, but that gets pretty complicated pretty fast. And so if you imagine that data sets are analogous to the files in a file system, then HDF5 provides kind of a directory concept. It's called a group. And the Python kind of equivalent data structure would be a dictionary. So you can have a series of nested groups, nested directories, nested dictionaries to organize your data sets according to whatever scheme you want. And in fact, there are standard schemes called conventions in different communities for sharing data from one group to the other. For example, NASA has spent a lot of effort developing earth science standards for sharing according to a certain specific format of groups and data sets arranged in the file. And actually, HDF5 does use the standard POSIX path syntax. If you want to access an object in the file that's in a couple of subgroups, then you can use the / separated path to get to that. The last thing that kind of makes it work here is metadata. And so HDF5 has a native concept of metadata. You can attach key value attributes to any object in the file, data sets, groups, whatever. And you're pretty flexible for what you can do that. Any supported HDF5 type can be used as a value of an attribute. So the best way to give you an idea how this really works is to give you just to show it to you. So I'm going to zoom over here. This is an actual data file from one of my experiments. I'm going to open this up here. This viewer program, by the way, HDF Compass, is itself written in Python and is maintained by the HDF group. So it's open source, and I recommend you check it out. So I open up the file here, and you see a whole bunch of different folders. These are subgroups. So the file itself is kind of like the root group, the / group in POSIX. And here you have a whole bunch of subgroups. And our accelerator kind of convention is, within our lab, is that one subgroup is one impact. So we fire a projectile, right, and it slams into a target. And then all of the experimental data from that impact is in one group. So we go ahead and open one of them. We'll open this one right here. You can see individual data sets stored within the file. So this is, for example, injected data set. This is a PMT in our experiment. And you can see over here that they have a shape and a D type. It's like a NumPy array. You can open it. You can see the data. You can actually plot it. Let's go ahead and plot it. This happens to be a light flash. It's a time series, right? So you'll notice that on the bottom of the screen here, this is not super useful. This is just the index of the data. And so there's metadata stored in here, and we store it. Our lab convention is to store a series of attributes attached to just the shot group. And so we open this, open as attributes. And you can see here's all the information that I need to do something useful with that data. So I got when the experiment was performed, I've got the speed of the particle, I got the mass of the particle, I've got the spacing in between the samples and the time series, and I've also got a whole bunch of other things from my analysis. This is, I believe, when the light flash happens. And so this is kind of an interactive process. You might have this kind of file open in Python, and you would update these attributes, and you would do various analysis things, and you write that data back into the file. So in Python, to give you kind of a sense for how it might look, this is kind of a short Python demo here for how to access this exact same file using the H5Py interface, which is one of the standard interfaces to HDF5 in Python. So you just go ahead and import it. You can install it through Conda or pip if you're feeling adventurous. And you can open up the file. And this, of course, is just, it's a little file proxy object. I mentioned before that groups that contain all these subgroups and sub-data sets follow the dictionary kind of protocol for accessing from Python. And so if we were to iterate over the file, over the root group of the file, what you would get is all the names of the various subgroups. This is just what we saw at HDF Compass. And so, of course, there are also methods on this file object for keys and items and I think update now. And of course, you can use the get item syntax to retrieve objects. So we can go ahead and retrieve. We could retrieve just one of these by name. You can also use the full name of the object to retrieve it. I'm going to retrieve one of these data sets, the one that we saw in HDF Compass, the light data set. So you do this. You retrieve it using the standard dictionary syntax, and the object that's returned is not a NumPy array. It's something else. It's a little proxy object. And the reason for that, again, is that you may have data sets on disk that are many terabytes, and so you don't want to dump all that into memory. And so the data set here is this proxy object. And so if you were to load all of it, you get a NumPy array. This is a standard NumPy slicing thing. And if you were to plot it, hopefully we'll see what we had on the actual thing. So there it is. And so, of course, if I wanted to do more sophisticated slices, I can do that. So here's if I wanted to do every 10,000th element, for example. And so what's going on here is actually very, very subtle. If you make this kind of a slicing command, what's happening is that H5Py is talking to HDF5, a C library, and calling a function that's provided just to do subsetting. So there's no reduction being done in Python. HDF5 is loading from the disk only those elements that meet this criterion. And so it's extraordinarily efficient. You don't need to worry about doing this manually yourself. HDF5 figures it out for you. So of course, the metadata is also trivial to access through Python. I can load a group object. This is the one that I was looking at for the metadata. This is also a proxy object, HDF5 group. And so there's an attribute object attached to this, attribute manager. And so it also follows the dictionary protocol. And so you can list the keys of this object, of course, are all the names of the attributes. And you can use the standard dictionary syntax to access the attribute values. And so HDF5, used in this kind of a fashion, is almost invisible. You don't need to worry about the fact that you may have several terabytes on disk or that you have all these attributes. You can interact with it just as if you were interacting with a NumPy array or a dictionary. So the kind of the last thing that I want to talk about here, I'll go back to my talk for just a minute. And so HDF5 is currently on version 1.8. And there is a version of HDF5 in the works called 1.10, which has been in the works for many years. And it is coming out in alpha form on, I believe, this fall, and then in final release will be in the spring. And there's a whole series of new features in here. I'm not going to talk about most of them. They're welcome improvements. But the one I wanted to talk about is this one here at the bottom, which is an improved mechanism for parallel processing in Python. As you know, in Python, because of the GIL, our approach to parallel problems is to use process-level parallelism. And so in HDF5, there's actually a very well-developed, mature approach for that. They use MPI, which is the message passing interface. This is what you would use on a supercomputer. And so it's very scalable. You can have thousands and thousands of cores all reading and writing from the same HDF5 file all at once. But there are some trade-offs. In order for this to work, there are some restrictions on how you can interact with the file. For example, creating attributes or groups has to be done in a coordinated fashion. And so for ad hoc problems or smaller problems, there's a lot of cognitive overhead as a programmer trying to figure out how to use this. And so if you don't want to use MPI, you can use one of the native Python approaches. There are many ways of doing this. For example, one is multiprocessing, built into Python standard library. And so the problem with that is you still have this issue where you have more than one process looking at one file, right? And so there has to be some kind of coordination because each one of them is doing some caching, for example, right? And so you can't just read and write from two processes. And in fact, at the moment, you can't even write in one process and read in the other one because of the caching problem. So what people do is they have one process dedicated to doing all the file I/O, and then they use queues, for example, to farm out the work to multiple processes, collect it back, and put it into the file. It's a lot of overhead for a programmer to have to write all that stuff. So in HDF5 1.10, there's a new feature called single writer, multiple reader, where you have one process that is doing reading and writing to populate the file, and you can have any number of processes looking at the file and pulling data out. And it's handled entirely by the HDF5 library through the file system. You do not need to write any code to coordinate the processes. And so as long as you open the file with the right mode in each process, it figures it all out for you. So this is great. This is coming out in HDF5 1.10. There is support for this in the HDF group Subversion repository right now. And HDF5 2.5 is contributed by a user. We actually have support for this. So if you're using an HDF5 trunk build, you can actually use this at the moment. And there is a page on the H5Py website telling you in detail how to build the correct version of HDF5 and the options that you need for H5Py to try it. So if you have this kind of a problem, I strongly recommend that you give it a shot and let us know what you think. So the next thing I want to mention here are some resources. So I mentioned that there are these two kind of standard interfaces for H5Py, for HDF5 in Python. One is H5Py, which I'm the lead author of, and so that's the one that I showed in the example. There's also PyTables, which is a more full-featured index-based system, and that is available at pytables.org. HDF Group, by the way, has gotten into Python in a big way over the last few years. They have a GitHub organization. They've got lots of code on there, including HDF Compass. And I strongly recommend you go to their website and check out their projects. Also a plug for my colleague John Reedy from HDF Group. He'll be talking tomorrow at 2 p.m. On a product doing HDF5 as a Python web service, which is a very cool project. So thank you for your attention. I'll take your questions. Great.
We have a few minutes for questions.
Sure. This gentleman over here.
So are there tools for detecting and ensuring data integrity and fixing files?
The question is, are there tools for checking data integrity and fixing files? It's a great question. Right now, there are tools from the HDF group that will allow you to verify a file's integrity. Right now, as far as I'm aware, there is no journaling in HDF5 files. And so I believe this is one of the projects they're working on for 1.10, but don't hold me to that. Yeah. This gentleman here.
How well does it do with non-numeric data, so text data or capital?
Sure. So you can handle text data as either a fixed length string like the NumPy array string, also as a variable length string. You can create ragged arrays where the strings have any length, which is kind of the most important thing for string data because you don't know how long it's going to be in advance. That can be used in any attribute in any data set. The standard kind of models are basically the same as HDF, same as NumPy. You have a fixed size, a fixed element size. So there's no higher structure than that. That's what I get. Sure. Yeah. Yeah. The question is, HDF5 files are difficult to back up, of course, because it's a big binary blob. That's absolutely true. It's kind of a hard problem to solve on the HDF5 end. I'm not aware of effort going into trying to resolve that, except that I will tell you that one feature in HDF5 1.10 will allow you to, instead of storing everything in one file, you can store data sets and so forth in various different files in the file system. And so this could be called virtual data sets, I believe. And so this could be a solution to that problem. That's true. The comment is I wrote a book on HDF5 and Python, which I did, and you should buy it. It's very good.
Just a quick question. What's the timetable for 1.10?
Oh, question is, what's the timetable for 1.10? It is alpha in the fall this year, and it will be production release scheduled for the spring of next year. But there is, again, it's in some version, and it's worth checking out at the moment. Yeah.
All right.
Great.
All right. Well, thank you very much.
Sure.